In the late 20th century, one assumption quietly dominated heavy industry. American engines were untouchable. They were bigger, louder, and forged through decades of industrial and military demand. But behind closed doors, that certainty was about to be tested, not by marketing claims or national pride, but by numbers recorded in test cells, shipyards, and industrial sites around the world. What began as routine evaluations soon unsettled long-held beliefs. Data emerged that didn't fit the story the engineers expected to tell. The results were debated, challenged, reinterpreted, and resisted. Yet they refused to go away. This is the story of the engine tests that were meant to confirm dominance and instead exposed a rivalry no one was ready to confront. The engine tests meant to prove superiority. By the mid-1970s, heavy industrial engines sat at the center of a quiet but consequential rivalry. Diesel power plants built in the United States by manufacturers such as Caterpillar, Cummins, and Detroit Diesel had long defined global standards for construction, mining, marine propulsion, and stationary power generation. Their dominance rested on displacement, torque, and durability, reinforced by decades of operation in harsh environments. Yet, as Japanese industry rebuilt and modernized after World War II, a new generation of engine manufacturers began pressing for recognition on technical performance rather than reputation. Companies including Mitsubishi Heavy Industries, Yanmar, Isuzu, and Hino Motors spent the 1960s and early 1970s refining diesel design around efficiency, precision machining, and thermal control. By the time international markets opened more fully in the late 1970s, Japanese firms were no longer content to compete indirectly. They wanted formal, head-to-head validation under controlled conditions. That demand coincided with growing pressure from buyers. Large contractors, shipping operators, and government agencies, particularly in Australia, Southeast Asia, and parts of the Middle East, were no longer satisfied with brand reputation alone. Fuel costs surged after the 1973 oil crisis. Emissions standards tightened, and uptime became as critical as raw output. Engine performance needed to be measured, not assumed. In response, a series of comparative engine tests were organized between 1976 to 1983, overseen by independent laboratories, maritime certification bodies, and industrial clients. These were not public demonstrations. They were controlled evaluations conducted in test cells, shipyards, and field installations, often tied directly to procurement decisions. The objective was explicit: determine which engines delivered superior performance under repeatable conditions. The tests covered multiple engine classes. Medium-speed diesel engines used in marine propulsion were evaluated alongside high-output industrial diesels designed for generators, mining trucks, and heavy equipment. Comparable engines were paired by displacement range, horsepower rating, and intended duty cycle. Japanese engines from Mitsubishi and Yanmar were matched against American units from Caterpillar and Cummins. All parties approved protocols covering load profiles, fuel quality, cooling conditions, maintenance intervals, and measurement standards. Early test programs took place in Japan, the United States, and Australia, often under the supervision of organizations such as Lloyd's Register and Bureau Veritas. Engines were subjected to prolonged load cycles, including steady-state operation, variable load response, thermal stress testing, and endurance runs lasting hundreds of hours. Metrics included fuel consumption per kilowatt-hour, thermal efficiency, vibration levels, wear rates, and operational stability. Expectations entering these tests were uneven. American manufacturers viewed the evaluations largely as confirmation exercises. Their engines were heavier, larger, and already proven in extreme conditions. Japanese manufacturers approached the process more cautiously, emphasizing compliance and repeatability. Engineers focused on calibration accuracy, fuel injection precision, and cooling efficiency, aiming to demonstrate consistency rather than spectacle. The first internal test summaries circulated in 1977, and they immediately unsettled assumptions. Japanese engines consistently met rated output while consuming less fuel than their American counterparts. Thermal profiles showed lower peak temperatures during sustained operation. Vibration measurements were tighter, and oil analysis after extended runs revealed a reduced particulate contamination. None of this suggested American engines were inadequate, but it challenged the belief that size and displacement automatically produced superior performance. Initial responses from U.S. manufacturers were measured. Engineers questioned calibration methods and break-in procedures. Some argued that Japanese engines were optimized for controlled testing rather than real-world abuse. Test administrators responded by extending run times, increasing load variability, and repeating measurements. The results shifted slightly, but the overall pattern remained. What complicated matters was consistency. Similar outcomes emerged across different facilities, operators, and climates. Marine engine trials conducted in Yokohama and Sydney reflected the same trends as stationary engine tests in California. Japanese engines were not outperforming dramatically in any single category. They were outperforming quietly across many. By 1979, the engine tests had taken on significance beyond procurement. They had become a comparison of engineering philosophies. American designs prioritized robustness and overload tolerance. Japanese designs emphasized efficiency, thermal balance, and precision manufacturing. The tests forced those priorities into direct confrontation. Despite rising tension, evaluations continued. More engines were added, duty cycles refined, and reporting standards tightened. The expectation was that enough data would resolve the issue conclusively. Instead, the accumulation of evidence made resolution more difficult. The tests had been meant to prove superiority. Instead, they revealed a deeper problem. When performance is measured carefully and repeatedly, it does not always align with expectation. By the close of the initial testing phase, one conclusion was unavoidable. These engine trials were not settling a debate. They were opening one the industry was not prepared to face. American confidence built on horsepower and history. Long before the first engines were mounted on test stands or connected to load banks, American manufacturers entered the trials with a deep sense of assurance. By the mid-1970s, the United States had dominated the global heavy engine market for decades, and that dominance was not theoretical. It had been forged in wartime production, post-war industrial expansion, and massive infrastructure projects that reshaped continents. Confidence was not merely cultural, it was historical. Companies such as Caterpillar, Cummins, and Detroit Diesel had built their reputations on engines that survived conditions others could not. From North American mines to offshore platforms and military logistics fleets, U.S. engines were known for one defining trait: they kept running when pushed beyond their limits. Displacement, torque, and structural mass were treated as insurance policies against failure. Bigger blocks, heavier crankshafts, and conservative tuning were not inefficiencies in this worldview. They were proof of seriousness. That legacy shaped expectations going into the comparative tests. Internal planning documents from American firms during 1974 to 1976 framed the upcoming evaluations as confirmation exercises rather than genuine challenges. Japanese engines were acknowledged as efficient and well-built, but often described as lighter duty or optimized for fuel economy rather than punishment. Many U.S. engineers assumed that once engines were subjected to sustained high loads, wide temperature swings, and long duty cycles, American designs would assert a clear advantage. Horsepower figures reinforced that belief. On paper, American engines often matched or exceeded their Japanese counterparts in peak output. Torque curves favored low-end pulling power, especially in industrial and marine applications. For engineers accustomed to equating performance with mechanical reserve, the idea that a smaller, more precisely tuned engine could outperform a heavier one seemed counterintuitive. There was also confidence rooted in geography. American manufacturers designed engines for vast, unpredictable operating environments: long-haul trucking across deserts, mining operations in extreme cold, and marine engines expected to run continuously for weeks. Japanese manufacturers, by contrast, were often perceived as designing for tighter tolerances, controlled maintenance schedules, and efficiency-driven markets. That perception, whether accurate or not, influenced how the tests were mentally framed before they even began. At early coordination meetings held in the United States and Australia in 1976, American representatives spoke openly about expectations. Discussions emphasized durability margins, overload tolerance, and survivability under misuse. Efficiency metrics were acknowledged, but rarely treated as decisive. The prevailing assumption was that fuel savings mattered only if an engine could survive worst-case scenarios, and American engines had already proven that repeatedly. This confidence also shaped preparation strategies. U.S. manufacturers focused on ensuring engines met rated output and structural specifications, trusting that inherent robustness would carry them through testing. Japanese teams, by contrast, were observed spending significant time on calibration, injection timing, and thermal management. To some American engineers, this attention to detail appeared excessive, even unnecessary. If an engine was strong enough, why worry about such fine adjustments? As testing approached, that mindset hardened. The trials were seen as an opportunity to reinforce market position, not redefine it. Some American executives privately viewed the evaluations as beneficial marketing tools, assuming favorable results would validate existing procurement preferences. The possibility of systemic underperformance was rarely discussed openly. Even early anomalies failed to shake that confidence. During preliminary shakedown runs, when Japanese engines demonstrated smoother load transitions or slightly lower fuel consumption, these observations were dismissed as irrelevant to real-world endurance. Engineers expected such differences to disappear once engines were pushed harder and longer. What went largely unspoken was how much identity was tied to the outcome. American heavy engines were not just products, they were symbols of industrial leadership. They represented decades of engineering tradition built around strength, redundancy, and mechanical authority. To question their superiority was, in a sense, to question the philosophy that had shaped them. By the time formal testing began in earnest during 1977, confidence had become an assumption rather than a hypothesis. Data was expected to confirm what history already suggested. Any deviation would require explanation, not acceptance. This mindset mattered more than anyone realized, because when confidence is rooted in legacy rather than measurement, evidence does not arrive on neutral ground. It arrives as a challenge, and as the first serious data began to circulate, it became clear that American manufacturers were not just defending engines. They were defending a worldview built on horsepower, history, and the belief that strength alone should always prevail. Numbers that disrupted the power narrative. When the first consolidated data sets began circulating internally in 1977, the reaction inside American engine manufacturers was immediate and uneasy. These were not polished reports prepared for customers or regulators. They were working documents, spreadsheets, charts, and engineering summaries compiled from early test runs across multiple facilities. Yet, even in this preliminary form, the numbers carried a weight that could not be ignored. Across test sites in Japan, the United States, and Australia, Japanese heavy engines were meeting rated output with a level of consistency that challenged long-standing assumptions. Under identical load profiles, engines from Mitsubishi Heavy Industries and Yanmar delivered stable power while consuming less fuel per kilowatt-hour than comparable units from Caterpillar and Cummins. The differences were not dramatic in isolation, but they were persistent. Fuel efficiency was the first metric to raise concern. In medium-speed marine engine trials, Japanese engines showed lower specific fuel consumption during steady-state operation and smoother transitions under variable load. American engines produced strong peak performance, but their fuel curves climbed more sharply during extended runs. Engineers initially attributed this to conservative tuning choices or calibration variants. Thermal data reinforced the trend. Temperature readings taken during prolonged load cycles showed Japanese engines operating with lower peak and average temperatures, particularly in cylinder heads and exhaust systems. Cooling systems stabilized more quickly after load changes. This did not suggest overheating problems in American engines, but it contradicted the assumption that heavier construction automatically delivered superior heat tolerance. Vibration measurements added another complication. Accelerometer data from test beds in California and Queensland revealed lower vibration amplitudes in Japanese engines across multiple operating ranges. Engineers noted reduced harmonic resonance at cruising loads, translating into lower mechanical stress over time. American engines, while robust, showed wider variance depending on load and operating speed. The most unsettling indicators came from endurance data. Oil analysis conducted after long-duration runs revealed lower particulate contamination and slower degradation in Japanese engines. Wear rates on critical components such as bearings and cam surfaces remained within tighter margins. American engines did not perform poorly, but their results showed greater spread. Some units exceeded expectations. Others required inspection or adjustment sooner than anticipated. What disrupted the narrative was not failure. It was reliability in the statistical sense. American engineers were accustomed to evaluating performance through extremes: maximum output, overload tolerance, and survivability under abuse. These tests emphasized averages, stability, and repeatability. When Japanese engines produced narrower performance bands across different facilities, operators, and fuel batches, it raised an uncomfortable question. Was superiority defined by surviving the worst moment, or by delivering predictable output hour after hour? By 1978, as additional data from marine trials in Yokohama and industrial generator tests in Western Australia were added, the pattern held. Different environments, different operators, similar outcomes. Japanese engines were not outperforming American engines by overwhelming margins. They were outperforming them incrementally, repeatedly, and across categories that mattered operationally. Initial responses focused on explanation rather than acceptance. U.S. manufacturers questioned fuel quality consistency, break-in procedures, and sensor calibration. Some argued that Japanese engines were tuned closer to optimal test conditions, while American engines were intentionally derated to preserve long-term durability. Test administrators responded by standardizing fuel supplies, extending break-in periods, and recalibrating instrumentation. The numbers shifted slightly, but not enough to restore confidence. Meetings grew tense as engineers debated interpretation. Did lower fuel consumption outweigh higher overload tolerance? Should vibration and thermal stability be treated as performance advantages or secondary characteristics? The same data supported different conclusions depending on which engineering philosophy guided the discussion. Japanese engineers remained restrained. They emphasized protocol compliance and repeatability, resisting any attempt to frame the results as victory. From their perspective, the data was simply describing reality without narrative. By 1979, it became clear that the power narrative built solely on horsepower was insufficient. Peak output still favored American engines in some classes, but the broader performance picture had shifted. Efficiency, thermal balance, and consistency were proving just as influential as raw strength. What unsettled American manufacturers most was how ordinary the disruption appeared. There was no dramatic failure, no catastrophic breakdown. The challenge came from spreadsheets and trend lines, not smoke or broken parts. The numbers did not shout, they accumulated. Those numbers did not end the debate. They ensured it could no longer be avoided. When efficiency became the controversy, by the time the testing programs entered their later phases in 1979 to 1980, the argument had shifted in an unexpected direction. The debate was no longer centered on horsepower, displacement, or even basic reliability. Instead, it narrowed onto a single, increasingly uncomfortable theme: efficiency. What had once been treated as a supporting metric was now driving the most intense disagreements of the entire process. Fuel efficiency quickly became the flashpoint. Japanese engines continued to post lower specific fuel consumption across comparable duty cycles, whether in marine propulsion trials, stationary generator runs, or industrial load simulations. The differences were not dramatic enough to feel like outright defeat, Yet, they were far too consistent to dismiss as coincidence. That subtlety made them especially disruptive. Efficiency gains accumulated quietly, translating into lower operating costs hour after hour. American manufacturers responded with growing resistance. Representatives from Caterpillar and Cummins argued that the tests placed disproportionate emphasis on fuel burn and thermal efficiency while undervaluing attributes critical in harsh operating environments. Overload tolerance, reserve power, and survivability under abuse, they insisted, were being overshadowed by metrics better suited to controlled testing than real-world use. At the heart of the dispute was a fundamental disagreement over what efficiency actually represented. Japanese engineers defined it as useful work delivered per unit of fuel, minimizing losses to heat, vibration, and friction. American engineers countered that efficiency without substantial excess capacity was fragile, that engines optimized too closely around ideal conditions risked failure when pushed beyond design limits. To them, inefficiency was not waste, but insurance. Test administrators were caught between these interpretations. The protocols had always included efficiency as a core metric, approved by all parties before testing began. Fuel consumption, thermal balance, and load stability were documented alongside output and endurance. Yet, as results accumulated, American manufacturers argued that efficiency was being elevated from one metric among many into the deciding factor. Thermal performance deepened the controversy. Japanese engines consistently operated at lower average temperatures during sustained load, reducing thermal stress and cooling demand. American representatives argued that higher operating temperatures were acceptable and sometimes preferable, given thicker components and conservative material margins. Lower temperatures, they claimed, did not automatically translate into superior durability over long service life. Emissions-related data added further tension. As emissions standards tightened globally during this period, American manufacturers maintained that regulatory compliance should be evaluated separately from performance testing. Japanese engines, benefiting from more precise fuel injection and combustion control, often showed cleaner burn characteristics. Critics argued this reflected tuning choices aligned with regulatory trends rather than inherent engineering superiority. As debates escalated, proposals to revise evaluation criteria emerged. Some U.S. manufacturers suggested weighting peak output and overload capability more heavily. Others proposed separating efficiency metrics from overall performance rankings entirely. Japanese teams rejected these ideas, pointing out that all parameters had been jointly approved before testing began. Changing them midstream, they argued, would undermine the credibility of the trials. The controversy spilled into technical meetings and review sessions. Engineers debated whether an engine that consumed more fuel but tolerated abuse better was truly inferior. Procurement specialists questioned how much inefficiency they could afford in an era of rising fuel costs. The same datasets were used to support opposing conclusions, depending on which priorities guided interpretation. What made the situation particularly volatile was that efficiency could not be easily dramatized. There were no broken components, no catastrophic failures to point to. Efficiency revealed itself slowly, in logs, averages, and cost-per-hour calculations rather than visible damage. That subtlety made it harder to confront and harder to dismiss. By 1980, efficiency was no longer just a measurement. It had become a proxy for deeper anxieties about engineering philosophy and market direction. Accepting the efficiency data meant acknowledging that precision, balance, and system integration could rival sheer mass and power. Rejecting it meant questioning metrics buyers increasingly cared about. Japanese engineers remained methodical, emphasizing repeatability and protocol compliance. American manufacturers grew more vocal, warning that efficiency-focused evaluations risked misleading buyers about real-world durability. Neither side accused the other of falsifying data. The conflict was sharper than that. They disagreed on what the data should mean. When efficiency became the controversy, the tests crossed a critical threshold. They stopped being a comparison of engines and became a debate over values, over whether performance should be defined by peak power at the limit or by consistency within it. And once that question was raised, numbers alone were no longer enough to settle the dispute. Retests under harsher loads and longer cycles. By 1980 to 1981, pressure to revisit the engine evaluations reached a breaking point. The original tests, though carefully structured and repeatable, were no longer accepted by American manufacturers as a fair reflection of real-world conditions. If Japanese engines continued to show efficiency advantages, critics argued, then the testing environment itself must have been too controlled. To settle the dispute, demands grew for retests that would push engines into harsher, more punishing operating conditions. Test administrators agreed to authorize a second phase, but under strict limits. The original results would remain part of the official record. Any new trials would add data rather than replace earlier findings. The intent was not to erase previous conclusions, but to determine whether more severe conditions would fundamentally change the performance balance. The compromise satisfied no one completely, but it allowed the evaluations to continue. The revised tests began in late 1980, introducing longer operating cycles and sustained high-load conditions. Engines were run at elevated output for extended periods, often exceeding earlier endurance thresholds. Load variability was increased to simulate fluctuating demand. Cooling tolerances were tightened, and maintenance intervals were stretched. These changes were deliberately designed to favor engines built around mechanical reserve and excess capacity. American manufacturers entered this phase with renewed confidence. Engines from Caterpillar and Cummins showed strong resistance to prolonged stress. Peak output remained stable, and major components endured extended operation without catastrophic failure. For U.S. engineers, these early results appeared to confirm long-standing beliefs that mass, conservative tuning, and durability margins defined true toughness. As operating hours accumulated, however, the picture became more complex. Japanese engines from Mitsubishi Heavy Industries and Yanmar showed expected performance degradation under harsher loads, but not collapse. Fuel consumption increased, yet remained lower on average. Operating temperatures rose, but stayed within narrower ranges. Most notably, performance variance across long cycles remained tight. The engines neither surged ahead nor deteriorated sharply. American engines, by contrast, displayed greater dispersion. Some units performed exceptionally well across extended cycles. Others required earlier inspections or adjustments as hours mounted. There was no systemic failure, but consistency became harder to ignore. Under prolonged stress, variability became more visible. Fuel efficiency quickly re-emerged as a point of friction. American representatives argued that higher fuel consumption under extreme load was an acceptable trade-off for durability and reserve power. Japanese engineers countered that efficiency under stress was precisely what long-term operators valued most. The retests narrowed the efficiency gap slightly, but did not eliminate it. Thermal performance produced similarly divided interpretations. American engines tolerated higher operating temperatures without immediate consequence, reinforcing claims of robustness. Japanese engines ran cooler overall, but with less thermal headroom. Critics framed this as fragility, while supporters described it as controlled operation. The same data supported both narratives. Extended cycle testing also highlighted differences in operational interruption. Japanese engines recorded fewer unscheduled pauses during long runs, largely due to steadier thermal and vibration behavior. American engines experienced more frequent interventions, not failures but inspections, recalibrations, and preventive adjustments. Over hundreds of hours, these interruptions accumulated into measurable downtime. By 1981, it was clear that harsher testing had not produced the decisive reversal many American manufacturers expected. The retests altered individual metrics, but left the broader performance picture largely intact. Japanese engines did not dominate under extreme stress, but neither did they falter. American engines remained powerful and durable, but not decisively superior. Rather than resolve the dispute, the outcome deepened frustration. Some American manufacturers argued the conditions were still insufficiently severe. Proposals circulated for even higher loads, longer cycles, or reduced cooling margins. Test administrators resisted, warning that endlessly escalating conditions would turn evaluation into destruction. The purpose of testing, they emphasized, was to measure usable performance, not to determine which engine could endure the most abuse. By the close of the retest phase, one conclusion was unavoidable. Harsher loads and longer cycles had not settled the argument. They had reframed it. The trials were no longer about whether Japanese engines could endure stress. They clearly could. The unresolved question was whether American definitions of real-world toughness aligned with how engines were actually used. The retests were meant to restore certainty. Instead, they reinforced doubt. Pushing engines harder did not erase earlier findings. It complicated them, and with each added hour of operation, it became clearer that no single test condition could deliver the decisive answer everyone wanted. Blame shifts to operators, fuel, and test conditions. By 1981 to 1982, the engine trials entered a new and more defensive phase. The focus moved away from hardware and toward explanation. With repeated tests failing to overturn earlier results, American manufacturers increasingly argued that the numbers did not reflect engine capability at all. Instead, they pointed to human factors, fuel variables, and test site conditions as the true sources of distortion. The machines, they insisted, were not the problem. Operator influence became the first major line of argument. U.S. representatives claimed that many operators involved in the trials had greater familiarity with Japanese engines, particularly in Australia and parts of Southeast Asia, where Mitsubishi and Yanmar units were already common. Smoother results, they argued, reflected operator comfort rather than inherent design advantage. Requests followed to restrict operators to those trained primarily on American engines, or to separate data sets by experience level. Test administrators responded by rotating operators more aggressively. Crews were reassigned across brands, duty cycles, and sites. In several cases, veteran Caterpillar operators were placed in Japanese engine installations, while operators accustomed to Japanese equipment were assigned American units. The expectation was that any operator bias would quickly surface. Instead, performance trends remained broadly consistent. Individual output varied, but aggregate patterns held. Fuel quality became the next point of contention. American manufacturers questioned whether fuel supplied at overseas test sites met the same standards assumed in U.S.-based evaluations. Variations in sulfur content, refining methods, and storage conditions were cited as potential explanations for efficiency differences. Japanese engines, critics suggested, may have been better matched to available fuel rather than inherently superior. In response, test administrators standardized fuel supplies wherever possible. Certified batches were sourced, stored under controlled conditions, and tested regularly for composition. Engines were recalibrated where necessary. These measures narrowed some margins, but did not reverse outcomes. Fuel explanations softened, but did not disappear. Attention then turned to ambient conditions. American engineers argued that temperature, humidity, and altitude differences across test locations subtly favored Japanese designs optimized for thermal balance. Cooler operating temperatures, they claimed, were easier to maintain under certain climates. Japanese engineers countered that trials had already accounted for environmental variables, and that similar results appeared across vastly different regions. As scrutiny intensified, test site procedures themselves came under suspicion. Questions were raised about sensor placement, data logging intervals, and averaging methods. Were transient spikes being captured fairly? Were shutdown thresholds applied equally? Test administrators reviewed protocols repeatedly, recalibrated instruments, and invited third-party observers to verify procedures. No procedural bias was identified, but trust continued to erode. What made this phase particularly charged was that none of the accusations alleged fraud. Instead, they suggested structural unfairness, subtle factors that, when combined, could tilt results without deliberate manipulation. The argument shifted from "the data is wrong" to "the data is incomplete." This distinction allowed disagreement to persist without direct confrontation. Japanese engineers expressed growing frustration. From their perspective, the trials had already absorbed extraordinary levels of scrutiny. Operators were rotated, fuel was standardized, conditions were documented. If results still favored their engines, they argued, then design differences could no longer be dismissed as artifacts. They cautioned that endlessly chasing alternative explanations risked undermining the purpose of comparative testing altogether. Buyers and procurement officials watching the process began to lose patience. For contractors, engines were rarely operated by ideal operators, fueled perfectly, or used under controlled conditions. Variability was the norm. From that standpoint, an engine that performed consistently, despite those variables, was not at a disadvantage. It was more valuable. By late 1982, the narrative had shifted decisively. Performance gaps were no longer framed as mechanical shortcomings, but as contextual misunderstandings. American manufacturers emphasized that their engines were built for abuse, not optimization. Japanese firms emphasized predictability under variation. The tests had become less about which engines performed better and more about which assumptions defined fairness. This shift had consequences. Every new data point was now filtered through suspicion. Strong results were attributed to favorable conditions. Weak results were dismissed as anomalies. The machines themselves receded into the background as debates centered on who was driving them, what they were burning, and where they were tested. In the end, shifting blame did not resolve disagreement. It prolonged it. Each explanation raised new questions. Each clarification invited further doubt. The trials continued, but their authority weakened as consensus slipped further away. By redirecting attention from engines to operators, fuel, and conditions, the controversy entered its most evasive stage. The question was no longer how the machines performed, but whether any test could ever be considered fair once expectations had already been challenged. Data, denial, and industry damage control. By 1982 to 1983, the engine trials had produced what most industrial evaluations aim for: a large, repeatable body of data. Multiple engine classes had been tested across different regions, climates, and duty cycles. Fuel consumption, thermal behavior, uptime, vibration, and endurance had all been logged in detail. Yet instead of settling the debate, the growing weight of data triggered a new phase, one defined less by engineering and more by denial and strategic control. Inside American manufacturing firms, the discussion shifted decisively. Engineers continued to analyze results, but senior leadership focused elsewhere. The concern was no longer whether the numbers were accurate, but what those numbers could do if interpreted without context. Internal meetings at companies such as Caterpillar and Cummins increasingly centered on messaging, customer perception, and risk containment. The data itself was not attacked directly. It was managed. Public statements adopted cautious language. Trial results were described as situational, preliminary, or non-representative of extreme operating environments. American manufacturers emphasized attributes that favored their engines but were not central to the trials: peak output, overload tolerance, and long-term survivability under abuse. Japanese advantages in efficiency and consistency were acknowledged only indirectly, framed as trade-offs rather than strengths. Privately, denial took more deliberate forms. Sales teams were advised to avoid detailed discussion of comparative data. Dealers were encouraged to emphasize service networks, parts availability, and brand familiarity instead of test outcomes. In internal correspondence, later referenced in industry publications, executives warned against allowing raw performance figures to circulate without interpretation. The data was not rejected, it was surrounded. Japanese manufacturers faced a different challenge. Companies such as Mitsubishi Heavy Industries and Yanmar were keenly aware that overt celebration could provoke backlash. Engineers were instructed to speak strictly in technical terms and avoid claims of superiority. Public communications emphasized compliance with agreed protocols rather than outcomes. The restraint was intentional, but it created space for others to define the narrative. Trade publications filled that space quickly. Coverage increasingly focused on controversy rather than conclusions. Articles highlighted disputes over methodology, operator influence, and test conditions, often presenting the trials as unresolved rather than evidentiary. This framing benefited manufacturers seeking time and flexibility, but it diluted the authority of the results. Damage control extended into procurement. During infrastructure and marine engine bids in 1983, American manufacturers submitted supplemental performance documentation drawn from independent or in-house testing, conducted under different conditions than the disputed trials. Japanese firms responded with audited trial data and long-term field performance logs. Procurement committees were left weighing not just engines, but competing interpretations of reality. Institutional resistance followed. Some U.S. manufacturers lobbied to exclude the trial data from consideration in government-funded projects, arguing that the evaluations lacked formal regulatory oversight. Others proposed new benchmarking frameworks or standards committees, effectively resetting the evaluation landscape. These initiatives were framed as calls for rigor, but critics viewed them as efforts to neutralize inconvenient evidence. Within engineering teams, tension grew. Some American engineers privately acknowledged that the data exposed real design trade-offs. Efficiency and system integration clearly delivered operational value. But acknowledging that openly risked internal conflict, the divide between engineering assessment and corporate positioning widened. Japanese engineers watched this response with unease. From their perspective, the data had not been disproven, it had been sidelined. Meetings once focused on performance graphs now revolved around interpretation and perception. Engineering discussion gave way to strategic framing. The trials continued on paper, but their purpose had shifted. For contractors and operators observing from outside corporate boardrooms, the contrast was stark. On job sites, engines either delivered predictable output or they did not. Fuel either lasted longer or it did not. Downtime either accumulated or it did not. Operational reality was simple compared to corporate explanation. By late 1983, the trials still existed, but their authority had eroded. Not because the data was flawed, but because acceptance carried implications few were ready to confront. Acknowledging the results meant conceding that long-held assumptions about power, dominance, and design priorities were incomplete. Denial did not mean rejecting the data outright. It meant refusing to let it stand alone. Every chart required context. Every conclusion demanded qualification. Damage control became less about hiding information and more about controlling how it was understood. In the end, the industry did not dispute the existence of the numbers. It disputed their meaning. And once interpretation became the battlefield, the debate was no longer about engines, it was about narrative authority. The data remained, the denial persisted, and the damage control ensured that even with evidence on the table, consensus remained just out of reach. Results that couldn't be engineered away. By 1984 to 1985, the engine trials reached an unspoken conclusion, not a formal ending, not a public declaration, but a point where further testing no longer changed the underlying picture. Engines had been retested under heavier loads, longer cycles, different fuels, varied operators, and harsher conditions. Protocols had been revised, instruments recalibrated, and interpretations contested. Yet the results themselves refused to disappear. The accumulated data showed clear limits to reinterpretation. Japanese engines from Mitsubishi Heavy Industries, Yanmar, and allied manufacturers did not dominate in dramatic fashion. They did not outperform American engines in every extreme scenario. But across years of testing, they delivered something harder to argue against: consistent efficiency, predictable behavior, and stable performance under variation. These outcomes persisted regardless of who operated the engines, where they ran, or how the test parameters were adjusted. American manufacturers had explored every technical avenue available to counter those findings. Horsepower ratings were emphasized. Overload tolerance was highlighted. Structural mass and safety margins were presented as proof of superiority. None of these arguments were false. Engines from Caterpillar, Cummins, and their peers remained powerful, durable, and highly capable. What could not be engineered away, however, was the growing recognition that raw strength alone no longer defined operational advantage. Attempts to contextualize the results continued. Efficiency gains were framed as marginal. Consistency was described as situational. Predictability was treated as secondary to survivability. Yet, these explanations weakened over time. Contractors and operators were less concerned with philosophical definitions of toughness than with cost per hour, fuel burn, uptime, and maintenance predictability. The data spoke most clearly in those terms. What made the results especially resistant to dismissal was their ordinariness. There were no catastrophic failures to isolate, no dramatic breakdowns to explain away. The Japanese advantage emerged quietly, in averages rather than extremes. Fuel logs showed small but persistent differences. Downtime accumulated unevenly. Thermal behavior remained steadier. Over months of operation, those details compounded into meaningful operational impact. By this stage, even internal discussions within American firms reflected a shift. While public messaging remained cautious, engineering teams increasingly acknowledged that the trials had revealed genuine trade-offs: precision manufacturing, tighter tolerances, and system integration produced measurable benefits. These were not anomalies of testing. They were design outcomes. Engineering could adjust future products, but it could not retroactively alter the evidence already recorded. Japanese manufacturers, for their part, remained restrained. There were no victory announcements, no aggressive marketing built directly on the trials. Engineers continued to emphasize compliance, repeatability, and documentation. The confidence was quiet, grounded in data rather than rhetoric. They understood that overt celebration would provoke resistance, not acceptance. Procurement decisions began reflecting that reality, often without explicit reference to the trials. Buyers weighted fuel efficiency more heavily. Long-term operating cost models gained influence. Predictability under mixed conditions became a selling point. The trials did not need to be cited directly to shape outcomes. Their conclusions had already filtered into decision-making. What the industry confronted, reluctantly, was a narrowing of escape routes. There were no remaining procedural flaws to correct, no variables left unexamined. Further testing promised only diminishing returns. At some point, continued resistance stopped looking like rigor and began to resemble avoidance. The results could not be engineered away because they were not the product of a single test, location, or assumption. They emerged from repetition. Every attempt to disprove them produced more data that reinforced the same patterns. Engineering solutions could respond going forward, but they could not erase what had already been measured. By the mid-1980s, the debate shifted from denial to silence. The trials faded from public discussion, not because they were resolved, but because they had become inconvenient. The industry moved on without consensus, carrying unresolved conclusions beneath the surface. Yet those conclusions mattered. They reshaped how performance was evaluated, how efficiency was valued, and how dominance was defined. The trials did not declare a winner, but they changed the rules of comparison. In the end, the most disruptive outcome was not that Japanese engines performed well. It was the results that endured. They survived scrutiny, reinterpretation, and resistance. They could be challenged, contextualized, and delayed, but not undone. Some data can be argued with, some can be reframed, but once results persist across time, conditions, and repetition, they stop being technical findings and become realities. and these were results the industry could no longer engineer away.